Hi, I'm Simon. I'm from Institute of Astronomy, National Tsinghua University. Recently, our paper is accepted by monthly notice, and the title is Photometric Redshifts in the North Ecliptic Pole Wide Field based on a deep optical survey with Suprime-Cam. And these are our collaborators. To begin with, I will give a brief introduction of our paper. To start with, I would like to ask the question, why is infrared important? To our astronomer, we want to review the high redshift universe by using infrared. However, most of the star formation is hidden by dust. And to be more specific, in Goto et al. 2019, he said that more than 90% at redshift higher than 1 is hidden by dust in our universe. So here I show you two images, one from visible light telescope and one from infrared telescope. In the left panel, you can see that in the visible light image, you can see the whole Carina Nebula. And this is actually the dust part of Carina Nebula. However, if you use infrared telescope, you can see through the dust and you can see the objects behind it. So this is the power of infrared. In our paper, we are using an infrared telescope which is called Akari. Akari has a very unique feature, which is it has a continuous 9-band photometry from near infrared to mid-infrared. So here you can see from the filter responses, there is no single gap in between the filter responses. And compared with Spitzer and Weiss, those very well-known infrared telescopes, you can see that there are gaps in between their filter responses. So in principle, Akari can detect those missing features which were missed by Spitzer and Weiss due to those gaps. So in 2012, Kim et al. He published a catalog paper about Akari's data in the North Ecliptic Pole Wide Field. In this paper, we have several data. So the big green circle here, I'm showing you the coverage of our Akari data. And this green region here is also known as the NEP wide field. And we also have some optical data. The first one is CFHT MegaCam, and this is a deep optical data. And the next one is Magnetic SNU Cam, and this is the swallower data compared with MegaCam data. Here I also show you a very small gray region here, which is our NEP deep field. So here you may notice that for NEP deep field we have two optical data, which is MegaCam data and Magnetic data. However, for NEP wide field we don't have both optical data. We only have the shallower Magnetic data. What's so important about deep optical data in NEP wide field is that we need to compute photometric redshifts in order to do scientific works. If we don't have enough photometric redshift, we will rely on SPECT data. However, for our 100,000 infrared sources, we only have about 3,000 SPECT data. So we don't have enough SPECT data for doing scientific works. That's why we need to do photometric redshift for those 100,000 infrared sources. And in order to compute photometric redshift, you need deep optical data to cover the whole NEP wide field. That's the problem we need to overcome. And I want to introduce some keywords to you, which is called Photo-C and also SPECT-C. SPECT-C is also known as spectroscopic redshifts, and it's basically finding redshifts based on features in spectrum. It is very accurate compared with Photo-C, but it is also time and money consuming. Photo-C is photometric redshifts. It's basically estimating redshifts based on photometric data alone. Compared with SPECT-C is less accurate, but it's much faster and less expensive. Many current and future survey only deliver photometric Also, spectrum of faint X is very hard to obtain. Therefore, we need deep optical data at NEP wide field so that we can compare velocity to do more future works with future survey. In 2014, Golo et al. We wrote a proposal to HSC to ask for deep optical data from HSC. And fortunately, we got data from HSC. And here I show you 4 cyan big circles here, which cover the big red circle, which is our NEP wide field. So eventually, we got deep optical data. And we can now estimate photometric redshift for this region. And to be more specific, I want to tell you how more sources from optical data we got. So the red dots are the optical data we had in the past, and those black sources are the new optical data we have in this particular diagram. And also for the depth of HSC G-band is so deep compared with MNRAS G-band data, which is only 25.5 magnitude. Our HSC G-band is 2 magnitude deeper than the previous data. And I want to introduce NEP MNRAS catalog, which is the catalog we're using in computing photometric redshift width. So this catalog is created by Songjin Kim, and this result is also recently accepted by monthly notice. We have around 100,000 sources in total, and sources with specs is only 22,000 in total. So the first thing we need to do is we need to try to check if there is any bias in our spec-C catalog. If there is, we need to correct it. So the first thing we want to check is the color diagram of our catalog. Here we plot different color diagram by using HSC bands. And we can see that for the red spec-C data and the gray photometric data, they are mostly consistent. So we don't have a very obvious bias between our spec-C data and our photometric data. However, we do have some bias based on different spec-C campaigns because our spec-C is from different spec-C campaigns. And also we have a bias to infrared axis because this is a current catalog. And actually this is our special point of our catalog. And also I want to mention one maybe problematic bias in our spec-C data is that our spec-C data is mainly biased to those brighter galaxies because that's the feature of spec-C data. We can only get brighter objects spec-C because it's easier and less expensive to do it. However, we do need to correct about this bias. So here we use a quote from Lima et al. They use a nearest neighbor method, which is a machine learning way to correct the bias between the spec-C data and photometric data. Here we input HSC 5 bands photometry, which we have the most data with, and we also input spec-C data, HSC 5 bands. So the gray part here is the spec-C data, and the orange part here is the photometric data. We are trying to shift this spec-C data magnitude distribution to the orange one by using this nearest neighbor approach. And the red one is the spec-C magnitude distribution after applying weight. So we can see that our spec-C magnitude distribution is now consistent with our photometric magnitude distribution after applying weights. And we also found a problem about magnitude discrepancy in the catalog. So here I show you the same source with different bands observed with HSC bands and also Akari. You can see that those cyan circles are actually different observation detections from HSC photometry. However, we only matched one of these to our Akari catalog. That means the detection from the same source of different parts of this galaxy is divided into several parts, and only one of the circle is matched with our Akari detection. In order to correct this, we also dig into the STD of this kind of examples. So we can see that Subaru HSC magnitude and HSC and CFHT MegaCam magnitude they have an inconsistency in their magnitude. Therefore, this kind of sources is not reliable to do scientific works. And we try to exclude those erroneous sources by using flag. Here we use the sigma of the magnitude difference between HSC I band and MegaCam I band, and also the sigma of HSC Z band and SNU Cam I band. For those sources which about the 5 sigma distribution, we put a flag on it. So therefore, in the catalog, you can see flags about these erroneous sources. And for users of our photometric data in the catalog, they can decide whether to use these sources for their scientific works or not. So here we are using LUFA for computing photometric redshifts. LUFA is the SED feeding code which can compute photo C. The first thing we did in the analysis of photo C is we compared different template models to find the best template model to compute it. And here we fixed 26 bands photometry to be our filter sets. We compared 6 different models, template models, to see which one is better. And here we can see that Cosmos performed the best with outlier fraction 16.3% and photometric accuracy 0.058. And the next thing we want to do is to compare different filter combination. Here we fixed Cosmos as our template model. And here I show different bar charts which is representing different filter combination. So here you can see that for setup 1, it is the best performance filter combination, which is also known as the 26 bands from Idenite SNU Cam to Iraq-wise near-infrared band. And also we need to separate star and galaxy in our catalog. In our paper, we use an approach which is using the chi-square value computed by LUFA. So here we are using stellar ICD templates from LUFA, and we use the chi-square Gale and chi-square star from LUFA. For chi-square Gale, it is the minimum chi-square values obtained with galaxies, and for chi-square star, it is the minimum chi-square value obtained when it is fitted to stellar templates. So in principle, when chi-square Gale is larger than chi-square star, it is a possible star candidate. And when it is smaller, it is a possible galaxy. So here I show you the performance of our star-galaxy separation by plotting a color diagram. You can see that for different color representing the different categories or different population in our catalog, star-galaxy separation. So here the red one are galaxies with redshift larger than 1, and the black one are the galaxy with redshift smaller than 1, and the green one are star candidates. You can see that by using our chi-square value, they have a very obvious galaxy trend and stellar trend, which is separated by the chi-square value. Therefore, we concluded that this star galaxy separation is quite successful. And the reason why we don't use size and stellarity because we do not want to confuse it with AGN, and so that we don't exclude AGNs from our catalog. And these are our models in Cosmos which we are using to compute PhotoC. So these are also showing the models in our catalog. The models we are using for computing PhotoC in our paper. And these figures you can find in the paper. Here I show you the most important figure in our paper, which is the PhotoC versus SPEC-C diagram. And this is the PhotoC versus SPEC-C diagram which have the best performance in our paper. It has around 2000 SPEC-C data we compare with, and with a weighted outlier fraction 11.3% and a weighted PhotoC dispersion about 0.053, which is quite good in our NEP wide field. We also show you the redshift distribution in histogram. You can see that we plot the SPEC-C distribution here and then PhotoC distribution here. To remind that this SPEC-C distribution is already corrected so that it is consistent with our photometric data by using weight. We also plot Cosmos PhotoC distribution, redshift distribution here, just in advance. And in our paper, we also compare our PhotoC performance with different paper, which was previously computed in the NEP wide field. In our paper, we compare our results with Oi et al., which was published in 2014. For the same redshift range and same NEP deep field data, our data is better, much better in terms of the outlier fraction, and with the similar photometric distribution. And most importantly, we have more data in our paper because we are covering the whole NEP wide field, and also we have applied a weight to our data, to our results, so that our paper is more reliable in terms of the bias. To summarize, in our paper, we computed photometric redshift by using 26 bands from optical to near-infrared bands. And our results for this PhotoC dispersion lower than 1.5 is 0.053. And our results for weighted outlier fraction lower than 1.5 redshift is 11.3% for about 2000 SPEC-C sources. Thank you.